I am in San Francisco, a city famous for cable cars, Alcatraz, and the stunningly beautiful Golden Gate Bridge. But this is also a city located directly in between two of the most active fault lines in America. The Hayward Fault lies 13 miles east of the city center. The San Andreas Fault is just 5.5 miles to the west. And the area's busiest commuter bridge, the San Francisco-Oakland Bay Bridge, runs right between the two. It was in 1989 when Loma Prieta hit San Francisco, a 7.1 magnitude earthquake that devastated the city. It interrupted the World Series, killed 62 people, and rendered the east span of the Bay Bridge, the third busiest bridge in the world, structurally unstable. The quake stretched the bridge apart, causing a 50-foot-long, 250-ton section of the upper deck to collapse. Crews repaired the damage and reopened the bridge a month later, but it was left vulnerable to a complete collapse in the next major earthquake. So right now, to protect the city, architects, engineers, and the government are coming together in the single largest public works project in the history of California. They're attempting to build a new Bay Bridge. Costing $7.2 billion, this 8-mile-long bridge, made up of two unique spans, is getting completely overhauled. On the west span, the double suspension bridge was flexible enough to survive the earthquake. All it needed was reinforcement. But on the east span, the original truss bridge was just too rigid for earthquakes and too weakened from the collapse, so it's getting completely replaced. The new span will be one of the most seismically advanced bridges in the world. An unprecedented type of structure, strong enough to withstand a magnitude 8 earthquake, by designing parts of the bridge to stretch and even break. So by design, you know what piece is going to break during an earthquake?
Yes.
Which is a very different logic than how the old Bay Bridge was built.
That's right. We are engineering the seismic performance of the bridge.
So while they were trying to make their bridge as robust and as strong as possible, in some ways, you're trying to make your bridge fail in specific places.
And engineered specific places, yes.
So you're actually controlling the failure.
Yes.
By channeling failure to specific areas, engineers can protect the key structural parts of the bridge, like the tower. The single tower will be unlike anything ever built, divided into 4 interconnected legs. They're joined by 120 shear link beams, which will move and absorb seismic energy deforming during an earthquake. The beams can then be replaced in just a few days, thereby protecting the tower from serious damage. It's the first time that this technology has ever been used on a bridge. So during an earthquake, when this thing starts to move, all the damaging force of that quake gets directed right here at these shear link beams.
That's right.
They break, you replace them, the bridge still stands.
That's right. And you design them like the bumper on your car. You're driving your car, you have a little accident, the fender deforms, but you can still drive your car.
So instead of trying to battle the earthquake, you're kind of just rolling with it.
That's right.
The new road deck is also designed to roll along with an earthquake. It can stretch more than 3 feet due to special hinge pipe beams embedded inside. These giant shock absorbers make the new span 9 times more flexible than the original Bay Bridge. But directing flexibility into these specific areas means the rest of the road deck has to be bound firm, so it won't be stretched apart in an earthquake. Crews working on the new span are joining together 28 individual bridge segments into one solid roadway through a massive job of bolting and welding. This is happening right now on the first 4 segments of the eastbound lanes, which will carry drivers into Oakland. Okay, so Daniel, we're now standing at the very edge of the segment. Yeah. And while the bridge